You may have seen that term octane before. It may be familiar to you, particularly if you drive or if you pump gas for somebody who does drive. It's on every gas pump. Minimum octane rating usually starts at 87 and goes up from there. And the higher the octane rating, the more you pay for your gas. Usually the higher octane ratings also have other things mixed in with the gasoline. Anybody know why you want a particularly high octane in your gasoline? Any car heads here know how that works or what the purpose of an octane rating is? I didn't know until recently. I had no idea until I looked it up. So that's a great idea. It is related to how it burns, yes. But it's not exactly the more bonds and the energy in that sense, although that might play into some things. So gasoline is a product of crude oil. It goes through this fractional distillation process. Gasoline comes off towards the top, but not at the very top in terms of the low boiling points. Lowest boiling points are going to be things like methane, propane, butane, things like that. Gasoline is going to have a mixture. It's not going to be a pure substance. It's going to be a mixture of different hydrocarbons. But the octane, amount of octane in the gasoline does make it more stable and less likely to, the more octane you have, the more stable and less likely to spontaneously combust at the wrong time. Now, this used to be more of a problem for older cars before we got fancy computerized fuel injection systems that do a pretty darn good job of deciding when and how much fuel and air to push into the combustion chamber at the right amount of time so that it fires and explodes, basically, at the right time to drive the pistons. In older cars, before fancy electronic fuel injector systems, you would get sometimes this thing called engine knock, which was basically firing at the wrong time that did not contribute to the smooth movement of the motor and the smooth movement of the pistons and thus the axles. And so you would get this thing called engine knock. It would sound like something was knocking on your engine because you'd have these explosions happening at the wrong time. And so increasing your octane level was one way to reduce engine knock. Again, that's less of an issue these days. Another way that was previously used, another additive that was put into gasoline for a long time was tetraethyl lead. So leaded gasoline had lead added to it so that it would reduce engine knock, among other things. Pardon what? But it turns out lead is really, really bad for you, and spewing out large amounts of lead in your exhaust and having just lead everywhere turns out to be very bad for your brain in particular. So we no longer use tetraethyl lead in gasoline. And there are other things that you get added to the like super special premium whatever versions that also have higher octane ratings. If you drive a modern car, it doesn't really matter that much. You're not getting that much bang for your buck by adding the special things that you can get for more money. If you're driving some sort of performance sports car, I suppose, maybe. I don't know enough about cars to really know where the break-even point is with that. But the minimum octane that they can sell in the U.S. Is 87. And there's a whole formula for calculating it, et cetera. So octane, though, if we're talking about it as it's actually not the straight chain octane that is the stable thing that keeps engine knock from happening, but we'll be talking about isomers possibly tomorrow. But if we had a straight chain octane, what would the molecular formula be? Based on the stuff that we did last week. Yeah, Amaya. Can you say that again? Okay. Okay. Yep. that would be the condensed structural formula. So and how did you figure out that it was going to be 6 versus some other number? Right, so we're going to have these methyl groups sort of anchoring either end, and since it's octane, that means we're going to have 8 carbons, just like an octopus has 8 arms. What is the molecular formula for octane? Yes, Kathy? Yes, so you could get that a number of ways. You could look at the pattern that we were generating as we went through successive lengths of carbon chains. You could draw it out and count up the number of carbons and hydrogens. You could use the formula, which says that if we have n carbons, then we have 2n plus 2 hydrogens, if I have a straight chain alkane here. So any of those would get you the molecular formula and then the condensed structural formula that tells you a little bit more about that structure. So we're going to continue with this today. Last time, good Lord. Last time we talked about how looking at alkanes, anything that has the A and E at the end, like methane, ethane, propane, was just going to have single bonds between carbons, if there are any bonds between carbons. And we were just going to have carbons and hydrogens. We weren't going to have any other functional groups. We'll talk more about those later. And we talked about these different ways of writing the formula, the molecular formula, the condensed structural formula, and the full structural formula where we're showing all of the bonds. Now remember that this is not actually what the molecules look like. And either tomorrow or Monday, I'm still deciding what order I'm going to go in next. We're going to be pulling out the model kits so you can see a little bit more what the 3D models actually look like. And we'll also be doing some stuff on a simulator online to look at that. But for our purposes, when we're drawing a structural formula, it's easiest to go with the sort of 90-degree angle approach. And so after we went through a bunch of those, we left off sort of starting to talk about having branches on our chain and how we could, instead of just having methane, ethane, propane, etc., we could have a methyl group or an ethyl group attached to a chain as a branch. And that naming that involved a couple of different things. Determining the name and structure for that involved a couple of different things. You're given a condensed structural formula written out, and we talked about how the parentheses here, especially when we don't have a subscript, but even sometimes when we do, more often is actually going to indicate that this is a branch off of the main chain coming off of the previous carbon. And so we talked about how we have a set of carbons here, 1, 2, 3, and 4 carbons in a line, and then we have this CH3, this methyl group, branching off of that third carbon. And we talked about how we name these branches, how we have to use a number to indicate where the branch is on the main chain. Well, first of all, we have to decide how long is the main chain. And we're going to name the molecule based on the length of the longest continuous chain. And so in this case, even though we have 5 carbons in the whole structure, we're not calling this a pentane, we're calling it a butane, because there were only 4 consecutive carbons in the longest chain. And so we had a methyl group coming off of one of the carbons, and so we called this a methyl butane. Now, we did also talk about numbering the chain, numbering the carbons in the chain, and how when we do that, we always want to start the numbering closest to whatever the branch or functional group is that we care about in the molecule. So rather than starting our chain over here as 1, 2, 3, 4, we started it closer to the branch so that our methyl group was given the smallest number possible. Okay. Now, and then we still keep the butane at the end. So rather than, we don't say methane and butane because it's not a full methane molecule, it's just a methyl group, the CH3, attached to that second carbon. We actually, in this one, I don't remember if I talked about this or not with you guys, we actually don't need the number for this one, okay? And typically, if you don't need the number, you don't put it in. The reason we don't need the number is that if this methyl group was moved to the next carbon over, we would just change the numbering so that it would still be coming off carbon number 2. And there's no difference because we've only got 4 here. There's no difference between carbon number 2 counting from the right versus carbon number 2 counting from the left. So it ends up being the same structure. And if we moved that methyl group over to one of the end carbons, then it wouldn't be a methyl group anymore. It would just be another carbon in the straight chain, and it would be a pentane. Okay, so I did the numbering to get you guys familiarized with that, but technically, you wouldn't even need to put the 2 here because there's no other way that you could have a methyl butane other than for it to be in position 2, as long as there's nothing else on the molecule. Okay. I don't think, I will have to double check on this. I don't think that the mark schemes will mark you wrong on this if you did put a 2 here. Okay, because there's a couple, there's a little bit of wiggle room with the naming on these. Right. Okay, so we actually did start with this last time. I did draw out the structural formula, but for anybody who wasn't here, or if it's been a while, I wanted to go ahead and restart this one. So here we've got our end anchor here. So we've got carbon number 1, we've got carbon number 2. Now we have a branch coming off of carbon number 2. And then we have carbon number 3. And then we've got 2 things coming off of carbon number 3. Okay. One of those is going to be carbon number 4. The other one is going to be a branch. So we're going to see how that plays out when we draw out the full structural formula. I'm just going to start with the carbons. So my second carbon has a methyl group on it. My third carbon has 2 methyl groups. I'm just going to go ahead and put this one down here to make it a little bit easier. I don't think that's what I did last time. So if you have it drawn with this carbon up on top, it doesn't really matter where they go, and for the alkanes anyway, and you'll see that when we play around with the molecular models. And then I can fill in my hydrogens. Gets a little messy, and we'll talk a little bit later about other ways to show the structure. There are a couple other methods that we use that make our lives a little bit easier and or make things a little bit clearer. So this is our structure. Now, in this case, again, our longest chain is going to be a 4-carbon chain. So that could be these 4 carbons here with 2 methyl groups off of the second and third. It could also be these 4 carbons with this being the methyl group off of the second carbon. There's no difference between those 2. I could draw it going from this carbon here Same idea. I still have a methyl group off the second and a methyl group off the third. I could draw it like this. Same thing. I still have a methyl group on carbon number 2 and a methyl group on carbon number 3. So, but the point of this is to say, make sure that you look for the longest chain, even if there's a bend in the two-dimensional structure here, because sometimes they will try to trick you. And they will give you a straight chain, and they will give you a branch that's bent that's actually longer than what looks like the straight chain. And so just make sure that you are looking for the longest possible chain of carbons. Now I'm going to go back to the sort of simplest one to look at here. And we're going to go ahead and number our carbons. Because the methyl groups are on the second and the third, it doesn't matter which way we number it, okay? If I go left to right, then I have 1 on the second, 1 on the third. If I go right to left, then I have 1 on the second and 1 on the third. It's exactly the same thing. Okay? Any questions about how I got to this full structural picture, or how I found the 4 carbon chain? Run with me on that. So now I've got 2 methyl groups. So, and they're on 2 different carbons. So I have to indicate that they're not both coming off of carbon 2, that they're actually coming off of 2 different carbons. So I have to give both numbers, both of the numbers that have a methyl group on them. So I'm going to name this as 2, 3. Okay, so before this one we did 2 dash methylbutane. Now I'm going to have 2, 3 dash, and I have to say that I have 2 of them, that they're both methyls. So I could have a methyl and an ethyl, or I could have a methyl and a butyl, or something like that. Although if it was a butyl, it would be a different, whole different structure. But in any case, I have to indicate that these are both methyl groups. I'm not going to write methyl. So this is where I get to go back to using the Greek prefixes, because it wasn't complicated enough to give you a whole new set of organic prefixes. We also have to go back and use the Greek ones as well. So this is going to be 2, 3 dash dimethyl butane. So this would be 2, 3 dimethyl butane. Tells me that I have 2 methyl groups. They're on carbon number 2 and carbon number 3 of the 4 carbon chain. Yes? Here? Over here? Oh, this. Oh, this is saying that there are 2 of these. So there's a CH3 coming off of here, and then there's another CH3 also coming off of here. So that's this carbon right here. This is carbon 3, and it's got 2 different methyl groups coming off. One of them is part of the butane chain. The other one is a branch point. Yeah, so that's, yes. That just means, and you can usually see, if you see parentheses, look at the carbon before it, and if it has, if it's not packed within 2 anchoring methyl groups like we talked about with the octane chain, then it probably means that both of those things are on that previous, coming off of that previous carbon. Mm-hmm. All right, this is one of those things where it's tricky, but it gets better when you practice it, okay? And it's also not a huge part of the question bank for organic, but it is important that you be able to recognize what these things are. I'm not going to give you pages and pages and pages of practice work. I will offer some of that to you as optional practice, but I don't want you to spend too much time on this. I just want you to get familiar with it and understand what these different pieces of the names and the structures mean. Okay. Okay, so there's a couple more, one or two more that you can do on that page, but I'm going to let you guys do that. I have an answer key already digitized that I will post after tomorrow in Canvas, so you can check your own work. What I want to do is move on to the next portion, which talks about the alkenes. So we've been talking about alkanes, and I told you that the ane ending means that there's only single bonds between the carbons. The ene ending means there's at least one double bond between the carbons. How do we know that the double bond has to be between the carbons? Because hydrogen can never have a double bond or a lone pair or more than one bond. Right. So if we see a double bond, it's going to be between the carbons. And the naming is very similar in that we're using the same prefixes. So there is no such thing as methene because there's only one carbon in meth, and so you can't have a double bond between carbons. But you can have ethene, which might ring a bell from Lewis structure days. The popular structure to make you guys draw. So here's ethene. It's two carbons, one double bond between them. We've got propene is three carbons, one double bond. Now this doesn't have neither of these have any particular numbers associated with them because we don't need them. Ethene only has two carbons, so there's only one place the double bond can be. Propene has three carbons, but if it's not between these two, if it's between the other two, then we just change the numbering, and it's exactly the same thing. Yes? I'm sorry? Correct. Correct. There's no resonance, yeah. We'll get into some resonance stuff a little bit later, mostly just with benzene. Once we get to 4, now we have to specify where the double bond is. And it's not part of a branch, so we're not going to say 1-butene, although you will see that as an acceptable name. And I believe that if you were asked to name this compound and you said 1-butene, they would not take points off because it is an accepted way of naming it. However, the technical IUPAC rule for naming it is that when we're talking about double or triple bonds, the number goes right before the suffix. So the number is going to bisect the butene. It's going to go right before the ene so that we know that that number 1 is the beginning of the double bond that makes it an ene. That way, if I also have a branch off of a different number, that'll go at the beginning, and it'll still be clear that the 1 was part of what was where the double bond goes. Okay, so this would be but 1-ene. Now, if I change this and made the double bond in the middle, that would now be but 2-ene, because it starts on carbon 2. So it's always wherever the double or triple bond starts is the numbering, okay? And that actually is a difference between but 1-ene versus but 2-ene, slightly different structure. Oops. Okay. And again, you're going to number the carbons. If the only thing in there is your double bond, then you're going to number the carbons so that the double bond is the lowest number possible. So when I said but 2-ene, it wouldn't be 3, it would be the first number at the beginning of the bond. Okay. And this is important because you may see a structure where you can draw a bigger carbon chain by not including the double or triple bond. But that is not acceptable, okay? If you have a double or triple bond, your longest chain must include that bond, even if you can draw a longer one without it. Because you can't have the double bond be an offshoot, be part of a branch. It has to be part of the main chain. So we're not going to call this a pentene, even though I can count even though I can count 5 carbons here, this is not going to be a pentene. It's going to be a butene because it has to include the double bond. So let's talk about how we would name this, this compound. So where am I going to start numbering the carbons? Am I going to go left to right or right to left? Right to left, because I have to have my double bond on the lowest number carbon that I can. So I'm going to start here with 1, 2, 3, 4. Okay, and now I've got this thing coming off as a branch. What kind of group is that? And it's maybe a little hard to see if you're in the back. Is that a methyl group? How many carbons are in the branch? 2. So what kind of group is that going to be? If it's 2 carbons? It's going to be ethyl, yeah. Just like 2 carbons would be ethane by themselves, a group, a branch with 2 carbons on it is going to be an ethyl group. So the ethyl group is coming off of carbon 2. So I'm going to say 2 ethyl. And then it's 4 carbons in the longest chain that includes the double bond. So that's going to be a butene. But I'm going to indicate that that double bond starts on carbon number 1. So this would be 2-ethyl but 1-ene. Now, you will occasionally see something like 2-ethyl dash 1-butene. This is more common, technically less correct, but this is they're saying the same thing, okay? And like I said, I believe that you would not get points off for writing it this way, as long as you didn't try to put the 1 up in the front, as long as you put the 1 next, as closer to the ene part, okay? So, all right, so if we look at the ones on your chart, first one's pretty straightforward. We just have carbon, 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 double bond carbon, and then the hydrogens to fill it out. Okay? At some point, I'm gonna assume that you know how to fill out the hydrogens. But be careful when you're doing that. And pay attention to the condensed formula if you're being asked to draw a structural formula, because this doesn't have 3 hydrogens on it, even though it's at the end. This one does. But this carbon already has a double bond. It only has room for 4 total. So it only has room for 2 hydrogens. And this carbon already has a double bond and a single bond, so it's only going to get 1. Okay, so make sure that with the double and triple bonds that you're paying attention to how many hydrogens you get. So regardless of whether you're going from formula to structure or structure to condensed formula. And then this is just We've already seen this. This is just our but1-ene, our 4-carbon chain with the double bond at the end. And again, we're always going to number, in this case, right to left, because we always want the lowest number to be where the double bond is, or closest to the double bond. Okay. All right, so there's some more practice options here. Again, not a ton, because I don't want you to spend the rest of your life learning how to name organic compounds. Plenty of time for that in your sophomore year of college if you're going to be pre-med. So I'm just going to leave it at that for now. And I want to go to section 4 real quick, which is the last part of this, the last sort of new part of this packet. The rest is just extra practice on the last 2 pages, going back and forth between names and structures. So the last bit that we're going to start with here, that is another very simple functional group. So we've talked about the alkyl groups having a branch on your alkane chain. We've talked about having the double bond, having an alkene. And now we're going to talk about our haloalkanes, where we're basically adding a halogen. And basically instead of a hydrogen. So it's just a question of which carbon is the halogen stuck to, and you're going to use the same numbering conventions that you used already. So pretty straightforward. Here we've got 1, 2, 3, 4 carbons, and then we got a chlorine on the last one. This is I apologize. I've probably said this before, and this won't be the last time I say it. I apologize for the terrible fonts that chemistry teachers and chemistry textbook writers and chemistry worksheet writers use. Almost anytime you see a C followed by something that looks like it could be an uppercase I or a lowercase l, 99.99% of the time it's chlorine. It's Cl. Okay? So you can pretty much just assume that unless it doesn't make any sense. Okay? So this is just going to be Cl with hydrogens making up the rest. And so this, we're going to name this the same way. So this is going to be 1 dash chloro. And actually it should be the other way around. This is going to be 1 because that's where the chlorine is. 2, 3, 4. So that's going to be 1 chlorobutane because there are no double bonds here. And note that, sorry, I should have said this earlier. Note that in our condensed structural formula, when we write it out, we do designate double or triple bonds in there because you have to. Otherwise, it doesn't make any sense. Okay. So if there's no double bonds shown, you assume that these are all single bonds. That's an alkane. And this would just be 1 chlorobutane. I do want to very quickly move on to the third one, which is where we have one of the rare occurrences in organic chemistry of an iodine in our condensed structural formula. So that is, in fact, an I, uppercase I. It is not H lowercase l. There's no such thing as HL. There's no element that way. So this is going to be an iodine that is on that middle carbon. Okay. Everything else, same thing if you have more than one. You're going to use the di-tri approach. You're never going to use mono to indicate that you have one methyl group or one chlorine. You're just going to leave it as chloro. But if you have 2 chlorines, it would be dichloro. Or if you have 3 iodines, it would be triiodo. Okay. Everything else in this packet should be doable. All right, so I'm going to let you work on that. I'm going to post the answer key tomorrow.